Right, now we start the last major topic. I think we're assured now that the loop gain is the central parameter. Everything depends on loop gain. From it, you can calculate everything to do with the closed loop properties, including input and output impedances and stability. The only other thing you need is the G infinity, but that's the specification, and that's almost trivial because that's the starting point. Everything else depends on T. So it's time now to talk about how you actually measure T. And we've already set up most of what we need to do to discuss this, because we've already modified the analysis method looking ahead to the time where we're going to need to measure it, which is principally we don't want to measure T by actually breaking the loop, because in practice that's very hard to do, and we found that the substitute, namely injecting the test signal into the closed loop, was not only a neat analytic technique, but it's also much better when it comes to the experimental end of it. So that's the part of it we're going to follow up now and see how you really do that. So again, when you're going to measure loop gain, the first thing you have to do is choose a suitable injection point. And it has to satisfy the same two conditions. It better be inside the loop, and also you have to inject it at a point where you don't upset impedance loading. So I'm going to use a separate little example now to measure that. And here's a small feedback amplifier built around an IC chip. And I won't go into the details of why it was designed this way, because that's not the problem that we want to look into now. We simply want to assume that we've analyzed the system and we're going to measure the loop gain and see whether we're right. So all we have to do at this point is do the analysis first to predict the loop gain, because as I've already mentioned, you always want to do that in advance. Otherwise, you may waste a lot of time taking measurements that turn out to be useless. So you always should have an idea what to expect before you start. So all we'll do with this is we'll do the analysis to find out what the predicted loop gain is. Okay, that means we still have to choose an injection point. And since we'd obviously like to match it on the bench eventually, that imposes some limitations on the choice of injection point, because we're not going to be able to do it inside the chip. So we're limited to an injection point that is outside, and we don't have many choices. One of them is the point P, because the data sheet says that the output impedance of the op amp is very low. I don't remember exactly what it is. It's a few hundred ohms. But anyway, it means that the output of the op amp is pretty close to an ideal voltage source, at least compared to what it's driving into, which is at least 20K. So it's not ideal, but it looks as though it'll be pretty close to ideal in order to do series voltage injection. Point Q would be equally good in principle, because even though looking back to the left, it's not an ideal source, but the source impedance looking to the left, if you made a Thevenin equivalent, would be less than 1K. And while that isn't zero, it's very small compared to the impedance looking the other way, which is the input impedance to the chip, which is in the megohm range. So that would also be a good point to do series voltage injection, but only in principle, because the dynamic range of available signal there is tiny. And so you'd have a lot of trouble with measuring signals in the noise and hum pickup and a lot of other stuff. So the point of choice is clearly the output of the op amp, where you have the full dynamic range available. So the first thing to do is the analysis, which means you draw the model. And after that, we'll be able to inject a signal, both on paper and on the bench, making the V1 0, and we'll have an injected voltage source at that point. That'll be the VZ. Okay, the circuit is explicit except for the gain of the op amp itself. So we look at the data sheet of the op amp. And the data sheet contains a simplified equivalent circuit. It also contains a graph showing what the gain of the op amp is for various compensating capacitors that you can connect outside. This is a full-size reproduction of that graph. Well, if you peer at it closely enough, you can see that the bottom line corresponds to a compensating cap external of 5,000 picofarads. But I'm not using 5,000, I'm using 100,000. Well, that's no problem, because obviously I can just scale this according to the factor representing the capacitances, because it's that capacitance that simply moves this low-frequency pole down in proportion to the value of capacitance. And then even in the graph they give, the pole is moved off the picture below 100 hertz. But that's okay. If I'm using an even bigger capacitor, all I have to do is scale it down by the factor of 20, and that will change the unity gain frequency from 1 megahertz down to 50 kilohertz. And the pole at low frequencies is moved even further off, but according to the same argument that we've talked about several times, I don't even care where that is. I don't care about the fact that the zero frequency gain will be finite. I'm not interested in it. The only important part of it from the point of view of the loop properties is what happens around crossover. So I don't need to write an equation that represents the gain of the op amp all the way down to zero frequency. All I need is an equation that represents this asymptote, which is going to influence things near crossover. And that's the standard single slope that we've done lots of times already. So the expression for the gain of the op amp is simply omega A over S that specifies a declining single slope, and the omega A is the frequency where the magnitude goes through unity. That's the unity gain frequency. That's all I need to represent the gain of the op amp. So I can go back to the diagram now. And draw that in. So I've labeled the gain of the op amp. A1 is omega A over S. Now I've got all the information I need to analyze for the loop gain, because I'm going to start with the Vx, which is at the right-hand side of the injected signal, and all I have to do is follow it around the loop to Vi and back to Vy using the gain of the op amp. And the loop gain is Vy over Vx. And I can split it into 3 factors for convenience. So I get a V2 over Vx is one of the factors. That's just a divider. And then Vi over V2 is another divider. And finally, the op amp gain is the third factor. And I can write all of those down pretty easily. And once again, we can anticipate a shortcut method. There's a capacitor out here that's going to cause some corner frequencies, and it's part of a couple of dividers. So the easy way to do it is to leave the capacitor out, find the midband value, and then put the capacitor in using the extra element theorem. So if at first I leave it out, then the factor V2 over Vx is a simple resistive divider, so I've called it A2. And the A2 is R4 parallel R1 plus R2 is the bottom branch, and the denominator is the same thing plus the top branch, which is the R3, and that factor is 0.31. Then the K factor is the feedback factor, which is the simple resistive divider, R1 over R1 plus R2, and the A1 is the op amp gain we have already. So I multiply those 3 factors together, and that gives me the loop gain, except I still have to put back the corner frequencies from the capacitor that I left out. Now, I left it out by replacing it with an infinite impedance, because it's in a parallel position. So again, mentally, we can go through all the steps of applying the theorem in order to restore it. Because it's going to give a pole and a zero, and each of them is going to be determined by the corresponding driving resistance. So all I have to do is calculate the driving resistance to find the pole, which is the RD, which is found under conditions of zero input and substitution of an independent source for the capacitor. And again, the only catch is you've got to be careful to identify properly what is the input. And we're solving for the loop gain. The input to the loop gain is the quantity in the denominator, which is Vx. So when I apply a second source in place of the capacitor in order to find RD, I have to put Vx equal to 0, which means the R3 is put in parallel with the R4 right across the RD, and also the R1, R2 divider is in parallel as well. So the RD is those three resistances in parallel, multiplied by the capacitor, and it gives you the pole. Now you find the zero the same way. You restore the input, which is Vx. You apply the independent source in place of the capacitor. You imagine those inputs are twiddled until you null the output. The output for T is Vy. You propagate the null back to the second source in order to see what happens to its current. If Vy is null, Vi is null, which means V2 is null. But that's right across the second source. So regardless of what current the second source drives in, zero voltage is developed across it, and Rn is 0. So there is no zero in the response. But of course that could have been seen to begin with also. Because this capacitor is right across a node through which the signal passes in determining the loop gain. So at infinite frequency, the capacitor will short the loop, and the loop gain will be 0 at infinite frequency for that reason. So the capacitor produces a pole, but it will not produce a corresponding 0, which is consistent with the detailed result that when you solve for Rn, the answer is 0. Well, I've gone through this sort of sequence of argument quite a number of times now. Maybe you're beginning to get a little happier about this extra element theorem. Even if you don't feel confident quite in getting it right yourself, maybe you can see yourself getting a little closer to it. That it's really not that bad. And this idea of null double injection, maybe that's getting a little closer to acceptability after I keep on going through it a few times, and all that happens is you have to do it a few times. Doesn't matter how many times I do it, it won't really get across until you do it. Okay, now we've got the result. You multiply these three factors together, and then you put in the pole factor that we've determined separately, and this is the result. So now you get a parameter multiplying these two coefficients together, which you can absorb into the omega 0 coefficient, because we've ignored the fact that there's a zero frequency flat gain, because we assumed the op-amp gain went to infinity at zero frequency, which we know it really doesn't, but it doesn't matter. So that's why the result comes out to have a 1 over S term, and there is no flat gain in front. And the other parameters simply determine what the omega 0 is. And you see the format for the loop gain is exactly the same as this basic general one that we've been talking about for a while. The loop gain comes down on a single slope because of the op-amp gain, and then it has a second pole, in this case because of the external capacitor. So this is the standard form that we've already talked about. So all we have to do is look up the result we got for what the closed loop gain is going to be, and we've solved that already. We know the closed loop gain is going to be flat, but it's going to roll off according to a quadratic, and the Q factor of the quadratic is determined by the position of the second pole relative to the crossover. And the definition of the Q is omega 0 over omega 2, which in this case is 0.56, or minus 5 dB, which means it's barely into the complex range. It's just a little bit above the break point between real and complex roots. And if you look up in that normalized graph, you find that the corresponding phase margin is 73 degrees, corresponding to the minus 5 dB for the Q factor. Well, probably this is an acceptable phase margin, giving rise to the acceptable closed-loop response. So it looks like this. Here's the loop gain coming down, actually from a finite value at zero frequency, but we've ignored that, crossing over at 1.4 kilohertz with a second pole at 4.4. And the phase angle that goes with it would be a fixed 90 degrees from the original slope, plus a minus 45 per decade slope centered on the second pole. And the red line is the sum of the two of them. And if you evaluate the phase lag at the crossover frequency of 1.4 kilohertz, you find that the phase margin is 73 degrees. I haven't actually shown that on the picture. So this is the prediction using the tentative values that we've set up. So the next question is, we want to make a real bench measurement of this and see whether the model's right and whether we've done the algebra correctly. Incidentally, if I go back to the first picture for a moment, and this graph, you may recognize what op amp this is. It's the old 709, the original IC op amp, the forerunner of all these things that we work with now. And I didn't mention that, but I used to write on this picture. I had mu A 709 in there. And then one time when I was giving this course, someone in the group said, well, I'm not interested in the old 709. That's obsolete. I don't want to hear about that. So he wasn't interested. So I tried to argue about why this was worthwhile anyway, but to avoid even the question coming up anymore, I blacked it out. We're now going to talk about how you measure a loop gain. So we're at the point in this particular problem now where we've predicted the loop gain we expect, and it has an adequate phase margin. So now we can go to the lab and breadboard the system and do the actual measurements. There's two parts to this. One part is how do you get the injected signal, and we'll talk about that in a moment. The other part is, once you've got the injected signal, how are you actually going to do the measurement? And we want to measure both magnitude and phase. So when you think about instruments that may be available for measuring phase angle, well, magnitude is easy. Any old voltmeter will do that. But measuring phase isn't quite so easy, and you may not have an instrument around. What you'd like to do is go to your company instrument library and check out a box that says phase meter on it. But you may not have one. So when you think of other ways to do it, there's various more fundamental ways, such as displaying both of the waveforms on a scope, dual trace scope, making sure that you trigger off only one of them, and then observing the relative horizontal position, which you can then used to determine the relative phase angle. That's all right in principle, but it only works in practice if both of the waveforms are nice and big and well out of the noise. Another way you might think of doing it is displaying one of the two waveforms on the vertical axis and the other one on the horizontal axis and generating a Lissajous figure. And that's all right in principle too, but it also requires both of the waveforms to be big and well out of the noise. Because if even one of them is buried in the noise, all you're going to get is a green screen. And that isn't much use. And even if you do get a nice Lissajous figure, it's more valuable for photographing and blowing up and putting on your office wall than it is for trying to determine the phase angle from it. In many cases, and again especially when we're dealing with switching power supplies, you have to be able to measure very small signals buried in a whole lot of noise. Because if you've ever dealt with a switching power supply, you know that its main output is noise. So you need to have some method of measuring a small signal down in the noise. And a narrowband voltmeter is certainly the first requirement to do that. Narrowband voltmeters are available as part of boxes known as wave analyzers or network analyzers. And a fairly low-cost one that I've used for a long time is a wave analyzer. Hewlett-Packard makes one, and it combines two functions. A voltmeter that has a narrow band in which the narrow band automatically tracks the frequency of a built-in signal generator or oscillator. So you don't have to worry about tracking the narrow bandwidth. It automatically follows the oscillator, and if you use that as a test signal, then the voltmeter automatically tracks it, and you can get a very wide dynamic range that way. In fact, the HP instrument that I use has a 90 dB scale on it. I think I mentioned that one before, in talking about observing the nulls when we do null double injection. Anyway, that's a pretty basic instrument and not that expensive. So it enables you to measure very small signals. Okay, the next thing we want to do is automate a little bit how we measure the magnitude and the phase, because it only measures magnitude. That particular instrument. Most voltmeters measure only magnitude. So what I've shown here is another historical method, so to speak, of doing this. The two voltages we want to measure, the ratio, both magnitude and phase, which is the loop gain, is Vy over Vx. So I put both of them into a dual channel preamp for a scope. You can see this is historic because this represents an old 500 series Tektronix. And what you have available is a selector knob that says you can observe on the screen either Vx or Vy. And Tektronix also conveniently provides a vertical output, so you not only look at the waveform on the screen, but you plug it into the analyzer, so you measure it also. And of course, to measure the magnitude of the loop gain at any particular frequency, you simply switch from one channel to the other and take the reading in dB and subtract the 2 dBs, and that gives you the magnitude of the ratio. That's straightforward. The interesting thing is that you can measure the phase angle as well, even though the voltmeter measures only magnitude. And the key to that is, remember, these two voltages that we're measuring are 2 out of the 3 that form a phasor triangle, because we could define the sum of the two as Vz. We've already done that. But it's the phasor sum of these two. And there's another knob on the front of the dual channel preamp that says sum or difference. Or maybe it only says difference, but there's another knob that says invert. So with a combination of the two, allow you to make a choice of whether you read the sum or the difference of those two waveforms. Which means by measuring differentially, you get a third reading on the meter, which is a magnitude also, but it's the magnitude of the third phasor. So what you do actually is measure the 3 sides of a phasor triangle. And then you dig back into your memories of old high school trigonometry, and you remember there is a formula that says if you know the three sides of a triangle, you can calculate the angles, known as the cosine formula. Maybe you've forgotten it. But anyway, you remember that it exists. And so that's what you can do in this case. So for each frequency, you measure the magnitude of Vx and the magnitude of Vy and the magnitude of Vz. And you plug into that formula and you find the corresponding phase angle of the loop gain at that frequency. Now, you can actually modify that by iterating the design technique, and you can refine it in order to overcome some difficulties to do with accuracy at certain conditions, but I won't stop to go into that. It's in some literature which I can tell you about if you're interested. But we needn't dwell on that, simply to point out that it's a technique that can be refined, and you don't even need to work out the formula. You just look up on a normalized graph to find the phase angle for different values of the three phases. So that's one way to do it. Now, of course, the easy way to do it is to buy yourself a network analyzer that does it all for you. And that's very nice, and there's quite a lot of choice of different models to do this. And the price you pay, of course, is they cost a lot more than simply the wave analyzer and the scope. But nevertheless, they do everything you want, and they give you digital readout of both the magnitude and the phase. And some of them are also computer controllable, so you can quickly go through a whole frequency run and get the answer in no time at all. So whatever instrumentation you want to use, you've got lots of choices, and you can trade off how much you want to spend on it. So that takes care of the measurement technique. Now, the remaining part of it is how do we get the injected voltage? So what we need is a floating source. So I'll put the analyzer back again. But the test signal output is usually grounded. Even if it's nominally floating, of course, it actually has a lot of capacitance to ground, so it's not very convenient. So what you visualize is that you need an isolation injection transformer, which basically converts a single-ended source into a floating output. And that's all right in principle, but then when you try to do this, you look into your box full of discarded components looking for a transformer, and of course you don't have one because you've never used one. And even if you did find one, it doesn't tell you anything about its properties. It may have an obscure part number on it, and that's about all. So you don't know the turns ratio, the magnetizing inductance, and the frequency response or anything. And in any case, it's probably 10 times bigger than the rest of the circuit physically anyway, and it does nothing but pick up hum. So this is not a very attractive solution. However, it turns out you do have an isolation injection transformer handy all the time. And it's called an AC clip-on current probe. And that's all it is. It's a transformer. Except normally you're supposed to use it to measure a current. And what you do is you clip it around a wire whose current you want to measure, and you put the other end of it into a termination or an amplifier, which converts the measured current into a corresponding voltage, and you can then read that on a voltmeter or an analyzer or whatever you like. But the AC clip-on current probe is a transformer, because inside the probe head is a magnetic toroid which is split in order that you can slide the head into two pieces and get the wire inside it. And what it is a one-turn primary transformer, where the one turn is the wire that you clip it around. And it's got lots of turns inside the head or around the toroid. I don't know how many turns. So it's got a big ratio anyway. And then the output goes into the termination. And it reflects current according to the turns ratio, like any decent transformer. But any real transformer works backwards. So what we're doing is plugging the probe into a signal source. And you clip it around the wire, and it works as a one-turn secondary isolation injection transformer. And it injects a voltage into the piece of wire. Not much, but you don't need much if you're using a network analyzer or wave analyzer with a big dynamic range. And that's all you have to do. This is the way in which you get the signal injection. And what you do in practice is you build your breadboard, closed loop, you turn on the power supply and it comes up and it runs, and you have this test instrumentation sitting on a cart somewhere, and your circuit is already up and running, and all you do is wheel up your cart full of equipment and you hang on 3 probes while it's running. You don't even have to turn it off to do that. And you're ready to go. And your control computer or your hand or whatever, you just go right along and do your frequency run. And you've not broken the loop. You don't have to fuss with applying a bias and adjusting it. And because of using a transformer to do the signal injection as well, you have nothing but 3 probes to hang on. That's all it takes. This is another of those things where I like to stop and ask you, have any of you seen this technique before? Well, really I'm asking more than one question. I mean, this includes measuring loop gain by injecting a test signal, and the second thing is this method of injecting the test signal. So, have you've seen both of those before? Well, this technique is becoming fairly widely known amongst the switching power supply community. Mainly because we've been talking about this for a long time. And we've been giving lectures and seminars and conference papers and so on for a long time about how to do this signal injection without opening the loop, and also how to use the current probe as an injector, but I didn't invent that. I didn't invent either of those, as a matter of fact, either the signal injection or the use of the current probe to do it. It's another one of those things that was actually published a long time ago and no one noticed. It was invented by Hewlett-Packard. And they wrote about it in an application note dated 1961. Another of those things that just passed on by. But you see, it applies perfectly well to any linear system measurement that you want to make. So if you didn't know about it before, it's a very useful thing. I might even go as far as to say that if you only remember one thing from this course, this is the thing to remember. Because compared to the conventional way of breaking the loop and establish operating point and applying test signals and all that, this is so much easier. Now, you might be a little concerned about how well this works. For example, what about the frequency response of the current probe, which is lousy? Doesn't matter. Because all you're doing is measuring the ratio of two other voltages, each of which is proportional to the VZ injected voltage. So the absolute value of the injected voltage or any of the others doesn't matter. All you're doing is measuring a ratio. So the only thing that matters is that the probe injects enough signal that the Vx and the Vy can be picked out of the noise by the analyzer. That is, you've just got to make sure you're within the dynamic range. But the frequency response shape is irrelevant. Now, certainly the probe response drops off pretty drastically towards low frequencies. In fact, it starts dropping off at several hundred hertz. It doesn't matter as long as you can inject enough to see the signal. And even if you run out of signal amplitude, there's plenty of room inside that probe to wrap that wire around it 10 times. And you make a 10-turn secondary injection transformer and you get 20 dB more signal. So you can extend the range quite a bit like that. Another thing that often bothers people is how can you get a voltage difference across a centimeter of wire? But don't be put off by only 1 centimeter, because that's how a transformer works. The winding is simply a piece of wire, and you induce a voltage in it by setting up a changing magnetic field from another winding. That's all this is. Now, again, power supply people don't have any problem with worrying about how you can get a voltage across a piece of wire. Because when you're designing, for example, a 100 amp 5 volt power supply, the secondary winding of the output transformer at the switching frequency is 1 turn, or maybe 2 turns, not of wire, but of copper foil, 1 inch wide. And you get 2.5 or 5 volts across that piece of copper foil. And there's nothing weird about that. So you needn't be concerned about getting a few millivolts across a centimeter of a skinny wire. The analyzer has no problem at all in picking it out. Okay, so much for the experimental technique. Let's go back to now to what you get for this particular example. Because what we've anticipated is, again, if I go back and find it, what we've anticipated is this. So we make measurements using one of these techniques, and what we find is this. And this is typical. Some of the measurements agree with the prediction and some of them don't. So what we've done is confirm the magnitude of the loop gain at low frequencies, and it follows the corner of the second pole, and then we get a deviation at higher frequencies. So what are we going to do about that? And your first thought may be, well, why bother? Because the deviation is a concave upwards corner, so we have a 0. And the 0 will give a little extra phase lead down at the crossover frequency, and so we'll improve the phase margin, which was already 73 degrees. So we needn't bother finding out where the 0 comes from. Let's just ignore it and go on and get production rolling. Well, unfortunately, when you look at the corresponding phase measurements, you see that's not correct. The 0 is giving an additional phase lag, not lead. So in fact, you're using up some phase margin instead of getting some more. And this suggests you'd better pay a little more attention as to why that 0 is there, because it's that old nemesis, a right half plane 0, that has a lag instead of a lead. And when you do the eyeball least squares fit business with your straight lines to determine where the corner is, it's 12 kilohertz. And you get a consistent corner frequency from the phase, except that it's a lag instead of a lead. So the result is the loop gain we originally thought just had 2 poles, and now we find it has a right half plane 0 as well, and it's going to use up 7 degrees of the phase margin. Well, where does it come from? Better find out now. Obviously, it can't come from anything outside the op-amp, because there isn't anything outside except a couple of impedance dividers. And there's no way that's going to give a right half plane 0. So you have to look inside the op-amp. So let's look at this simplified diagram. And you don't have to look very long to find out that there is one of the interstages here, which is a common emitter. Actually, it's a Darlington common emitter, but basically the same thing. And the compensating cap, which is outside, is actually a feedback cap between collector and base of a common emitter amplifier stage. And we spent a lot of time already discovering that the basic common emitter amplifier stage with a collector base capacitance has a right half plane 0. And when we were talking about that, we said, well, it's a very high frequency, so we don't need to bother about it. But I also suggested that there may be some cases where that frequency could come down to a region where it could cause some problems. One of the occasions where it could come down is where the collector base capacitance is not the 5 picofarads that's inherent in the transistor, but you may have purposely put a much bigger one outside. That's exactly what I did. I put 100,000 picofarads outside. And that's what brought the right half plane 0 down all the way to 12 kilohertz. Now, when I look more carefully at this data sheet, you see that I did something wrong in the design, because the data sheet said I should have put a resistor there as well. In fact, it's labeled on these asymptotes. I neglected to do that, on purpose, of course, in order to illustrate this point. Because what happens if you put a resistor in series with that cap? It limits the effect of the capacitor. In particular, as frequency goes to infinity, the cap will become a short, and you'll be left with the resistor. Now remember, the reason you get a right half plane 0 is because you have a parallel non-inverting signal path that dominates at high frequencies, reversing the phase. And so when you put a limiting resistor in series with it, you limit the gain of that path to be less than the gain of the other path, so it doesn't take over. So you don't get a right half plane 0. And that's the reason the resistor ought to be in there. But treating this whole thing as part of an example of the iteration of the design, analyze, measure sequence, what I'm doing, you see, is giving a simple example of doing that, where we have a prediction, we made a measurement, we find some partial discrepancy, we'd better go back and find out what was wrong. And that's what we've done here. What was wrong was that resistor ought to have been put in there, and it wasn't. Okay, so I've used that example as a vehicle to show a number of things. In particular, the implementation of how you get a series voltage injection to make a loop gain test signal. And you can use an AC current probe backwards as a one-turn secondary isolation transformer. A word of caution that I'm sure isn't necessary here: don't use a DC clip-on current probe, because it ain't a transformer. It's a Hall effect device. Hall effect devices don't work backwards like this. Well, the last thing we talked about was how to do series voltage injection in order to measure loop gain by using the clip-on AC current probe backwards in order to get a admittedly small injected signal, but it doesn't matter if it's small as long as the instrumentation can pick it out of the noise. Now, we know already there's a dual form of injection. That is, if you're not using a point where you have an ideal voltage source, if instead you have a point where there's an ideal current source in the model, then you use the dual injection form, which is a shunt current. So we also need to look at how you implement that in the practical case. So just as an example, let's go back to this audio amplifier that we'd had before, because in this is a case where we chose to do current injection. And the point where we did the injection was at the secondary of the final output stage, because we'd modeled everything before that point into an equivalent current generator, and the only thing left externally was the load and the feedback path. So this was the point which had labeled Q. That's where we did shunt current injection on paper. So if we want to do this in practice on the bench as well, what we have to do is have a current source injected at that point. So the two things that we have to take care of in order to do that: one is we don't want to upset the DC bias conditions. In this case, it wouldn't matter because this point is at DC ground anyway. But in general, if it were some other point, all we have to do is put a large blocking capacitor in there. So this separates any problem of upsetting operating point. Now we have to implement a current source. Well, most of our signal sources are actually voltage sources, and so all you have to do is put a huge resistance in there and drive it from your voltage source. Then the measurement that you're going to use is a ratio of IY to IX. So you use two clip-on AC current probes, IX and IY, another one over here. And you use them in the normal manner as current measuring devices. You put them into the terminations or the amplifiers, and you convert the outputs to voltages, and you measure the magnitude and phase using exactly the same instrumentation as before. So it's actually easier to implement current injection than voltage injection. Okay, so that's all I need to say about that. Now, we got one major topic left to talk about, which is to go back to the question of what is an ideal injection point. There are two conditions. You have to inject inside the loop, and the injected signal must add to the forward signal without affecting the impedance loading. The first one is obvious and it's easy to implement, but the second one is the one that in practice may be troublesome, because in fact, of course, you never can find a really ideal injection point. The real system is always going to have some non-zero output impedance from a voltage source. It's also going to have some non-infinite output impedance from a current source. So this is the last major point we have to look into now. What degree of ideality is necessary in order to get the right answer? Once again, if we go back to this little power amplifier model as an example, this was the first version of the equivalent circuit that we came up with. And we looked at the relative merits of injecting a voltage at point P, where it's in series with an ideal voltage source, which was acceptable, versus injecting at a point Q, where it's an ideal current source, and we did current injection. And I said more or less arbitrarily, let's do current injection, just to illustrate that method, which allows us to get rid of this internal loop and simplify the problem. But let's go back and look at what would happen if we did do voltage injection at point P. We could do it analytically, but we couldn't do it on the bench, because point P doesn't exist physically. Because the RB, 4.5 ohms, actually represents the output impedance of that driver amplifier. So you can't get at this point. So if we were in a situation where point Q didn't exist either, and this is always going to happen in practice, we still have to come down and look at what happens if the ideal point is not accessible. So in this case, I could put these green boxes around here to indicate that you can't get inside that box. The output impedance of the driver is buried inside, and you can't get around it. So sooner or later, we have to face the fact that we're going to do the injection at a non-ideal point. So let's see what happens. Obviously, the thing you do is get to the nearest possible accessible point. But still, we have to allow for the fact that there's going to be a non-zero impedance. So let's look at that question now. Once again, we don't want to clutter up the problem with unnecessary stuff. So all we need to identify in the problem is the loop where we're going to do the injection, the circuit loop. So we have a voltage source, and it's going to feed into some impedance. And so far, it's an ideal voltage source. All of the rest of the feedback loop we can bury inside this blue line again. We don't care about all the details of what goes on. But we do want to get into the problem where we start the right parameters that we want in the answer. So if we're going to do voltage injection at an ideal point, we've already shown this is equivalent to breaking the loop and applying the voltage at the same point. It's ideal still because we have a zero impedance out here. The first parameter to get into the answer is the loop gain, because that's the answer ultimately we're looking for. So how do we set up the problem to do that? The loop gain is Vy over Vx. So if I calculate it from this circuit diagram, how does that happen? Suppose the current I1 down the Z is the controlling current for this generator, which is what all the rest of the loop is doing. Remember, the UI is 0 at all times when we're working on the loop gain. So the relationship is I1 is equal to Vx over Z. I1 activates this generator, and I'm going to label the generator T times Z, I1, because that voltage is Vy. Therefore, if I divide Vy by Vx, the answer is T. And that's the correct answer because this is the ideal injection point. So all I'm saying here is I don't need all the rest of the loop. All I need is to identify the value of this generator in terms of the answer that I want to get. So I could have done it a longer way. I could have called this anything else. I could have called it M I1. And when I go through the resulting answer, M would turn out to be equal to TZ. So I've simply made that substitution at the start. I've labeled the generator with the parameter that gives me the right answer. I do that to simplify the problem and get rid of all unnecessary things, because the problem I'm interested in is what happens when I can't get to this point. But I've already got the desired answer embodied in the setup of the problem. Okay, just to review the first step, we've shown that injecting the signal into the closed loop at the ideal point also gives the right answer, as well as applying the signal at the ideal point. For the same reason, I1 is Vx over Z. I1 multiplied by Z gives Vy, therefore Vy over Vx is equal to T, and you get the right answer. Okay, now I'm going to modify this problem to consider the case where we don't have an ideal source. So the first thing I'm going to do is redefine the Z box as being two Z's in series, Z1 and Z2. Obviously nothing is any different, except over here I have to write Z1 plus Z2 in place of the Z. So the next thing is, all I'm going to do is move the Z2 out of this box and move it along this horizontal line. I'm just going to change its position in the picture, which of course makes no difference whatever to the answer. At the same time I've separated the two boxes, I've taken away all the surrounding clutter to do with the feedback amplifier. It's not necessary anymore. All the important stuff is embodied in this picture. So once again, I can say whichever injection method I use, whether I apply the test signal to that point, I get the right answer, and if I inject the test signal at that point without breaking the loop, I still get the right answer, because the equations are still the same. Now comes the crucial step when I can't get to point A. Now, the only point I can get to is point B, because the Z2 often is inseparable from the signal source, and I can't get to that point. And now I ask a question, what happens if I inject the test signal at the nearest available point, which isn't ideal anymore? Do I still get the right answer for Vy over Vx? Is it still equal to T? Well, that's a very simple problem to work out. I1 is Vx over Z1. That activates this generator. So I substitute for I1 Vx over Z1. But the value of that generator is no longer Vy. I have to allow for the drop in Z2. So I know the current in Z2, it's also Vx over I1 because it's the same loop current. So what I do is I evaluate this generator in terms of Vx, and then I subtract the drop in Z2, which I also know in terms of Vx, and this is the answer you get for Vy over Vx. Well, we were unlucky. It isn't T. So you get the wrong answer for measuring Vy over Vx if you can't get to an ideal injection point. But it's certainly worthwhile doing this, because now we know what it is we do get. And obviously, if Z2 goes to 0, then it reduces to the right answer because you're reducing it back to the ideal case again. But if it's not ideal, it tells you how small the Z2 has to be in order to get close enough to the right answer. And the first thing you notice is it's not the absolute value that matters, although you could have guessed that anyway. It's the ratio of Z2 to Z1 that matters, which in the interpretation of that is, when you're searching for an injection point, what you have to check is the ratio of the output impedance of the source looking back into the loop from the injection point to the impedance looking into the loop the other way. It's the ratio of Z2 to Z1 that matters. If it is small enough, the measurement of Vy over Vx will be close to the true value of T. Well, I've labeled what you measure a T sub V, because it is different from T. So I call that T measured by voltage ratio resulting from voltage injection. Well, you might say now, well, that's too bad that the signal injection technique didn't work. If you can't get to an ideal point, maybe we'll have to back up and go to the original method, which is breaking the loop and applying a test signal. And we'll have to give up the benefits of not breaking the loop, but if we can get the right answer that way, maybe we have to anyway. So let's see what happens if if you break the loop at a non-ideal point and apply the test signal. So that's sort of back to the original method. Okay. Vx appears across Z1. I1 is Vx over Z1. That activates this generator. You multiply it out. And this time that generator is equal to Vy because there's no drop in Z2 because you've broken the loop. Well, unlucky again. Still not the right answer. It's a different wrong answer. But it's still not right unless that impedance ratio is low enough. Now, this may seem a little odd because you say, why does Z2 come into this? Since it's dangling. Why is the answer wrong when Z2 isn't doing anything even? The answer is it's wrong because the right answer does depend on Z2. So what you've done by breaking the loop is you've eliminated the effect of Z2, but it really belongs in the correct answer because it's part of this divider ratio that gets you from this generator to the signal at this point in the normal closed loop condition. So the interpretation is Z2 does belong in the answer. It's inside T properly, and it's not being properly accounted for if you break the loop at that point. Okay, well, so much for voltage injections, either by breaking the loop or injecting it into the loop. What about current injection? After all, if we have a non-ideal point, who's to say whether we should use voltage or current injection? So maybe current injection works. So, again, if we're restricted to a non-ideal point, let's try current injection instead. Incidentally, you may have noticed that all of these injecting sources that I've been showing in the last several minutes have been non-ideal injecting sources. Because if we're going to account for a non-ideal generator inside the actual circuit, we better also account for the fact that our injecting source isn't ideal either. And the same with the current. So we've got an impedance in parallel with the current injection. Okay. We're going to measure Iy over Ix, call it a ratio T sub I, and the question is it equal to T? And when you go through the same little derivation and solve for Iy over Ix, unlucky again. It isn't T. But it tells you what the ratio of the impedances has to be in order to get close enough to T. And you see it's a dual result. Not surprising. And the only difference is it's the ratio upside down that matters this time. Z1 over Z2 has to be small, which is the same thing as saying that the Z2 has to be a very high impedance, meaning that this works when you have a current source and not a voltage source on the left-hand side, which we already know is the ideal case when you would use current injection anyway. And just to fill out this whole thing completely, if instead of injecting the current into the closed loop, you go back to the earlier method of actually breaking the loop and applying the test current, notice that the dual form of this is that when you break the loop, you do it by shorting the output rather than opening it, and then you apply an independent current to the break point, and you follow that around the loop and see what Iy over Ix is, and still unlucky. Still the wrong answer, a different wrong answer than before, but wrong nevertheless. So we now have tried all of the symmetric possibilities. So what we've discovered is loop gain T can be calculated or measured by either applying the test signal to the broken loop or injecting the test signal into the closed loop. Method 2 is preferable because it bypasses all the problem of operating points and so on. However, you still have this difficulty that all of these give you wrong answers unless the impedance ratios are appropriate. So here's the constraint that we still have to retain. In either method, certain inequalities have to be satisfied by the impedance ratio Z2 over Z1, where Z2 is the impedance looking back into the loop, Z1 is the impedance looking forward into the loop from the injection point. And here are the various inequalities. Now, for any injection point that you're considering, the only thing that matters is this impedance ratio. So once again, that's the only thing I'm bothering to write in the diagram. The only thing that matters. So if I'm going to determine loop gain by breaking the loop and applying a test voltage, I'm going to get the wrong answer, but it will be good enough if the impedance ratio Z2 over Z1 is small enough, which means much smaller than 1. I'm just summarizing all the things we just found. On the other hand, if I don't break the loop, but instead I inject the test signal into the closed loop voltage, I get the wrong answer, but it's a different wrong answer. And still, if Z2 over Z1 is small enough, I can get close enough to the right answer. But notice now what those conditions are. Z2 over Z1 has to satisfy two inequalities. The ratio has to be much less than 1, but it also has to be much less than t itself, because you have to be able to drop that ratio from two different places in the equation. Now notice at different parts of the frequency range, one or the other inequality becomes dominant. At low frequencies, the loop gain is large. So the first inequality is the most stringent one. But when you're measuring loop gain beyond crossover, t now becomes less than 1, and the second inequality becomes the important one. So you have to worry about both of them at different parts of the frequency range. That's half of it, and then you have the same things to say with respect to current injection. Same generalized amplifier, but if you're considering doing current injection now, you still have two choices. If you break the loop and apply an independent current, you get the wrong answer, but it will be close enough to the right answer if Z1 over Z2 is much less than 1, which is the reverse inequality from what it was for voltage injection. That confirms what we knew already. They are mutually exclusive. Only one can possibly give you the right answer, but maybe they're both wrong. They certainly won't be both right. Okay, and the final possibility is if you don't break the loop, but you inject a test current, once again, you have to satisfy two inequalities. The ratio Z1 over Z2 much less than 1 and much less than t itself. And there's the summary of all that. Now, you may think I'm overemphasizing this business about impedance ratios, but I've done that on purpose because, as I mentioned, this technique is becoming more widely known now in the power supply community. And I also mentioned that Venable Industries will provide the instrumentation to do this and some literature that goes with it and so on. And people are adopting this injection technique, and they are forgetting about these constraints. That's why I've put down all of these possibilities. Even breaking the loop gives you wrong answers if you don't observe these inequalities. That's a little surprise to some people, you see, because they think, well, of course you get the right answer if you actually break the loop. But I've tried to emphasize all along that you've actually upset the loading when you do that, and it gives you the wrong answer unless the loading is negligible, which is the same thing as saying you have to meet these inequalities. And just to drive that home even further, let's go back to this example we already used initially to introduce the technique of loop gain measurement by signal injection. Here's the circuit. We chose P as the injection point. We predicted a loop gain that had 2 poles. And then we made measurements, and we discovered that there was a right half plane 0. And then we found out where that came from, and we're satisfied with that and say, well, fine, everything's all right. Unfortunately, if you simply continue the measurements up to higher frequencies, everything is not all right again. The loop gain turns around and goes back up. Now, that's a little distressing, because if you've designed a feedback amplifier whose loop gain turns around and comes back up at higher frequencies, who's to say whether it may come actually back above 0 dB again, which means you'd have to satisfy Nyquist all over again, maybe up in the megahertz region. In other words, you may have potential instabilities up here, and we can't tell from the measurements because my wave analyzer ran out of range down here. So I can't make any measurements up at that frequency. But nevertheless, it would be very unwise to simply forget about this and turn it over to production and forget about it. Because now you're setting up the condition where a month or 2 later the consultant gets the panic phone call, you see. Anyway, not only is it distressing and surprising that the loop gain turns around and comes back up, it's even more surprising that there is no deviation in the corresponding phase graph. Well, now we have this situation where we've made a prediction. We make some measurements. Some of them agreed, some of them they didn't. We went back and iterated the analysis, and we found out we could improve the agreement. And we make some more measurements, and we still get a discrepancy, so we have to iterate again. And remember, whenever you get a discrepancy, they fall into one of 2 classes. Either the measurement was wrong or the prediction was wrong. The first time we found the discrepancy and iterated it, it was clear that it was the prediction that was wrong. That's why we had to go back and recheck the model. This time around, it's the other thing that's wrong. But we're not sure about that yet. But we better consider it. For one thing, if you get measurements of loop gain that do this, it's not too likely that the loop gain really does that. Because we haven't seen any op-amps whose gain turn around and come back up at very high frequencies. In fact, we'd be very happy if someone could give us one of those. So it's not likely that the loop gain really is doing that. And so we'd better check into the other possibility that we're not measuring what we think we're measuring. And the most likely reason for that is that the measurement we've made by injection of a voltage at a point in the loop, it's turning out maybe that it isn't an ideal point. And maybe we're not satisfying those impedance inequalities, which means we are not really measuring the true loop gain, we're measuring something else. So that's the thing we need to go back and check up. Well, if the problem is that the impedance ratio is no longer small enough, since we're doing voltage injection, what we need to do is go back and actually find out what the impedance ratio is. Now remember, Z1 is the impedance looking forward. And it's easy to see from the diagram what that is. It's R3 plus R4 parallel C parallel R1 plus R2. So it's easy to figure what Z1 is. You don't have to measure it. The Z2, looking back into the IC, that's the one we're not sure about. I said earlier on, in justifying the selection of this operating point, I said the data sheet says the output impedance is very low, a few hundred ohms. I neglected to say the data sheet gives it at only one frequency. So maybe that's the culprit. So what I did was I made an independent measurement of the output impedance of the op-amp. And I can calculate the Z1 looking in the other direction. So using my measurements of Z2, dividing them by Z1, I can actually predict what the ratio Z2 over Z1 is. And it's this. Z2 over Z1 is a small number, K sub Z, minus 64 dB. That's less than 1 over 1,000. But it comes up at higher frequencies. Not because Z1 goes down, but because Z2 goes up. In other words, the output impedance of the op-amp rises at higher frequencies. In fact, it looks inductive. Again, an example of where you get the property of an inductance, and there's no real inductance there. But it's to do with the internal structure of the op-amp. It behaves inductively. So maybe it's coming up high enough that it's invalidating the approximation. So what we really measured is T sub V, which involves this impedance ratio and also the true T. Now, from these measurements, I can find that even at the highest frequency of measurement, Z2 over Z1 is still a lot less than 1. I haven't actually noted it on this picture, but this is less. This is minus 64 dB down here, and that's at 8.3 kilohertz, and the highest measurement frequency was 600 kilohertz. So let's say it was 830, that would be a factor of 100. So by gain bandwidth trade-off, the magnitude at this point would be 100 times bigger than it was down here, which means I have to add 40 dB, so it's still minus 24 dB. So it's still much less than 1, even at the highest frequency. So when I look at what I measured, Z2 over Z1 is much less than 1 over the entire measurement range, so I can still drop it out of the first term, but maybe it's the second one that's causing the problem. And indeed, when I go back to these measurements, what I'm looking at now is the measurement that I'm making is actually just the sum of the true T and the Z2 over Z1 ratio. So if I superimpose the Z2 over Z1 ratio on the same picture as T, well, that's probably what the problem was. Because what I'm measuring is really the sum of T and the impedance ratio, and because it's the sum of two functions, whichever one is the bigger one is going to dominate. And that looks as though that's what happened. In other words, the true value of T became so small that even though the impedance ratio was small, it wasn't small enough, because one of the inequalities is Z2 over Z1 has to be much less than T, and it wasn't. So it looks as though that's the right answer. But we haven't quite followed up everything yet. Why wasn't there a change in the phase? So let's look into that. So we're starting now to look into this question. We want to add these two functions analytically and see whether it predicts the phase that we've actually measured. And so now T is this expression, including the right half plane 0, and the impedance ratio is that expression. And you may recognize now, although it's so long ago, perhaps you've forgotten it, this was the example I had in the introduction of how to simplify an analytic problem by doing it on the graph, by making suitable approximations. Because if I try to solve this analytically, I have to cross multiply and I get a cubic equation in S, which is going to be a nuisance. But this is exactly the same graph that I had in the introduction, illustrating this problem. I know what the answer is at low frequencies, and I know what the answer is at high frequencies, and the only part I don't know is how it makes the transition. So I don't care about what goes on down here. In other words, I can approximate the analytic expressions to be valid only for frequencies which are much higher than all three of those corners, which is what I've done right here. This is the same expression, except I've simply dropped the 3 ones, which is okay as long as S is much bigger than all 3 corner frequencies. So when I do that, now I cross multiply and I collect powers of S, and I still get a cubic equation, but there's no constant term. So I can factor an S out of the whole thing. And what's left behind is a quadratic. And I know what that corner frequency omega c is, because I get it when I factor the S out. When I factor it out, omega c is equal to this stuff. So I know what it is analytically. The square bracket is now identified as a multiplier on the high frequency asymptote for T. In other words, that high frequency asymptote for T is this one. And the square bracket tells me how the measurements turn that corner. And I've now solved for that. So I can get the complete result again for the sum by simply restoring the ones in front of those S terms that I dropped out in order to get the answer. So I can go back to this expression, and I simply put the ones back again. So here is the restored T in front, and here is the square bracket, which is the correction factor that I just solved for, and I can factor it immediately because there's no middle term. And it factors into a left half plane 0 and a right half plane 0 at the same frequency omega c, which I also know analytically, and I put the numbers in, and it's 81 kilohertz. Now that explains everything that was measured. Because it explains why the measurement of T sub v started to deviate from T at 81 kilohertz, and it turned around according to a double real 0 at the same frequency. So at that frequency, the -1 slope was changed to a +1 slope. But it also explains why there was no change in the phase, because the only difference is a right and left half plane 0 at the same frequency, and the phase contributions cancel. One's a lead and one's a lag at the same frequency. So that is now a full interpretation of the measurements. So the conclusion from this little exercise is, if you predict a loop gain from a system you're designing, and you then make measurements and you get a discrepancy between the measurement and the prediction, one of the reasons might be your prediction was wrong and you better go back and check your model and your analysis. But another possibility is the measurement was wrong. Not wrong in the sense that the measurement itself wasn't correct, but wrong in the sense that you weren't measuring what you thought you were measuring. That's more subtle and therefore more dangerous. And as you see in this example, if that happens, one of the things you need to go and check is, were you measuring the right thing? And the most likely thing that has happened is that your injection point is no longer satisfying those impedance inequalities, because you have to satisfy them at all frequencies because the values change. So when you get a discrepancy over part of the frequency range, that's where you need to check to see whether that ratio is still meeting the necessary condition. So again, summarize that main point. Okay, we got one more thing to do now. Here's another example of a feedback amplifier. It's exactly the same circuit as the one we talked about already, and the only difference is numbers, some different values. So the analysis is the same. Remember, just to review how we did it, we chose an injection point at the output of the op-amp, did series voltage injection, split the loop gain into 3 factors, calculate them separately using the extra element theorem to restore the capacitor after leaving it out at first. And the result, once again, is a loop gain that has an initial single slope, because we still neglected the flat part at 0 frequency, and it has a second pole. And since the only difference is the numbers, the only difference in the asymptote graph is that now the second pole comes in before the extrapolated crossover, which is still part of that general case that we solved earlier on, except that the closed loop discrepancy factor now is still a quadratic, but it has a high value of Q, because the second pole is now at a much lower frequency. And when you plug the numbers in, the Q is 4.5, 13 dB. And that corresponds, of course, to a very small phase margin, only 14 degrees. Now, of course, if you've done your design and you put the numbers into this point and you get this sort of answer, there wouldn't be any point in going into the lab and building it, because this obviously would be unacceptable. But for the purposes of illustration, let's go ahead and do that. So, if I build it on the bench, at least it's going to be stable because the phase margin is positive, even if it isn't small enough. So I went into the lab and I built it with those numbers, and I turn on the power, and disaster strikes. It sits there and oscillates with a huge amplitude, plus or minus 15 volts at the output, because that's what the power supplies were, and so that's all there is to limit the amplitude. Okay, now I'm talking about this because this has happened to all of us at one time or another. You try to build an amplifier and you get an oscillator. And what is the usual response to this? Well, you get your little box of junk capacitors, and then you pick one out and you start jabbing it down onto your breadboard. And then you find one that stops the oscillation, and then you look at it and see how many picofarads it is, and then you write it into the blueprint and send it off to production. Well, that's an exaggeration. I know you guys don't do that. Well, as you can imagine, after all this time, I'm not going to recommend that's the proper way to go about fixing the problem. Because even if you fixed it, you don't know that it's going to stay fixed if you don't know what caused it. And certainly something must have been very wrong with your analytic prediction, since it was supposed to be stable and it wasn't. So to follow the proper procedure, which is what I've mapped out already, there is a discrepancy between the measurement and the prediction, a rather gross discrepancy in this case. And so what you would like to do is to measure the unstable loop gain so you can see where it differed from what you predicted. Then you can pinpoint what the cause was and correct it. But now you have another problem. You can't measure the unstable loop gain, because while it is sitting there oscillating, it's driving itself nonlinear, and the model isn't what it was when it was stable. Now that doesn't mean you couldn't measure a loop gain. You can measure the loop gain by injecting the signal in the usual way and using a network analyzer to measure the resulting voltage ratio, because the network analyzer is narrow band and it will reject the oscillation and it will measure only the test injected signal. So you can get a perfectly good looking plot by measuring the unstable loop. But the trouble is it isn't right, for the reason I mentioned, that the loop isn't the same as it was before it was oscillating, because it's driving itself nonlinear. So that method doesn't help. So what else might you think of? Well, we have to stop it oscillating if you're going to make a useful measurement. So suppose you jab your little capacitor down somewhere until it stops oscillating, then you can measure the loop gain. And that still doesn't help, because the loop gain, again, is different from what it was when you designed it. So you're not measuring the correct loop gain then. So then you might have some grandiose ideas of using the extra element theorem backwards. Now that you've measured what it is with the extra capacitor, maybe you can work back to what it was before you put the capacitor there, which is the answer you're trying to get. But that doesn't work either, because something was grossly wrong with your original model, and to find the effects of the capacity you've added, you would have to know what the driving point impedances were where you put it, which still means you'd have to know what the original model was, and you don't. So that's a dead end. So it looks as though, after considering all of those possibilities, that you're between a rock and a hard place. There's nothing you can do to measure directly the unstable loop. Well, here's the last point that I want to make, which is appropriate for the end of the course, because this is like a gee whiz solution. So you can do this. You can measure the actual unstable loop gain directly. So I'm going to show you how to do that. And the key to it is, cast your mind back to not very long ago, when we were talking about injection points for voltage and current and breaking the loop and not breaking the loop and all those things. And I mentioned, sort of as an aside along the way, if we're talking about non-ideal injection points, we better also talk about non-ideal injecting sources. So I said, I'm putting this impedance in series with the voltage source, and I'm doing the same thing when I put current sources there. I'm putting an impedance in parallel with it. So I've included, I've incorporated non-ideal injecting sources all the way along. So I mentioned that, and I went back to what I was doing. But now you see what has happened as a result of including those non-ideal sources. Nothing happened. It never showed up in the answer. Never showed up anywhere. I didn't even give it a symbol. Now I put one on there. The ZV, even if it's non-zero, makes no difference to the measurements that you're making. So you don't have to inject a signal from an ideal source. Not only not nearly ideal, it can be a long way from ideal. It makes no difference. This is the key to measuring an actual unstable loop gain. What you do is, you do in fact have to change the loop in order to stabilize it and be able to make any measurement. And the key is, you change the loop and make it stable by changing it at one specific unique point. namely at the point where you're going to do the signal injection. In other words, you put that extra impedance in there. So here's the circuit we built, and it's unstable when it's closed. So now, in order to stabilize it, you insert an extra impedance. Not just anywhere, but you insert it at the place where you are going to do signal injection to make the measurement. Because that is the one unique, only place where you can put an extra impedance in and not change the measurement. Now, that still may seem a little surprising, but let's follow it through. I actually did this. This was sitting here oscillating, and so I take a few resistors and I start sticking them in, and 2.2K doesn't stop it, and 3.3 didn't, and 4.3 didn't, and 6.8 did. So I went a little further. Doesn't matter. I put 10K in there. Now it's quiet. It's stable. So now, at the same place, I inject my test voltage source with the AC clip-on current probe, and I make sure that my measurement probes are on opposite sides of the combination. And now you see I've set up exactly this condition. This is the output of the op-amp, which I've already chosen as being close enough to an ideal point. This is the impedance that it's all looking into, which is at least 10K. This is the extra 10K I put in to stabilize it, and this is the clip-on current probe. And I've already shown that by measuring Vy over Vx, I get the right answer for the loop gain independently of whatever that extra impedance was. Now, you still might be a little mystified as to why this works. And maybe the best way to explain that is, when you put the impedance in there, of course you really do change the loop gain. Let me go back to the previous picture with the impedance by itself. This is what you do when you stop it oscillating. When you put that impedance in there, the actual loop gain is, of course, changing, because you're making the divider ratio out here smaller and smaller. So the loop gain is falling. And in fact, in the limit, if you made that impedance infinite, you've opened the loop. And it better stop oscillating. So what has happened is that, true, the actual loop gain has changed and become stable. But what you measure is the original Vy over Vx, which has not changed. It's the impedance in the middle that makes the difference between the original unstable loop gain and the new stable one. But the measurement, Vy over Vx, and you can easily convince yourself, if you start with Vx and you follow it all the way around the loop back to Vy, that function is exactly the same. That has not changed by the addition of the ZV. But that is the function that used to be there when the loop gain was unstable. So that's what you measure. So that's how you measure an unstable loop gain. Well, let's follow through with the example, because the purpose of doing this is to know what was wrong with the model that you started with. So the prediction was that the loop gain ought to look like this, which ought to have had a positive phase margin, and so it should have been stable, but it really wasn't. And so when we measure the unstable loop by this technique, this is what we get. And of course there's a deviation this time. That's why it oscillated. But now we find out what the error was by doing the old eyeball least squares fit again, we discover that there actually is a third pole at 22 kilohertz. Now, does that confirm that it should have been unstable? Yes, it does, because the original phase margin was 14 degrees. But the third pole is going to contribute an additional phase lag at the crossover frequency of arctangent 8.5 divided by 22, which is 21 degrees of phase lag. So the phase margin becomes -7. Therefore, it's unstable. So the benefit we have from all this is that we've identified what the mistake was. Now you have to track that back and see why it happened. And once more, we've got to go back and look inside the op-amp again, and I've lost my transparency. Yeah, it is back here somewhere. Once again, we go back to this. Now, in this circuit, remember I changed the values from the first one, and I went back to the 5,000 picofarads that was corresponding to this lowest asymptote in here. But once again, on purpose, I left out the series resistor. So once again, I get the right half plane 0. Now, the third pole showed up at 22 kilohertz, which is on this diagram down here somewhere. Now, this asymptote in the data sheet did not show a pole at 22 kilohertz. Why not? Because putting this resistor there puts a 0 in the response together with this capacitor, and, surprise, 5,000 picofarads and the specified 1.5 K gives you a corner frequency at 22 kilohertz. So the IC chip designer said, when you put a capacitor of 5,000 there, you'd better put a resistor of 1.5 K as well in order to give a 0 in the response, in order to cancel the 22 kilohertz pole that is somewhere else. And that's why it doesn't show up, because it was purposely designed to cancel it out. But when I neglect to put that resistor in there, that 22 kilohertz pole, which is somewhere else, is no longer compensated, and it showed up in the result. And that's what made it go unstable. So that's completed the process in order to illustrate this design, analyze, iteration stuff again, and that's the last point. You can, in fact, measure an unstable loop gain. And you do have to stabilize the system first, but you do it in a very particular way which allows you to measure the original loop gain before you stabilized it. So that's a useful technique. It gives you more power over the final results. So that's essentially the end of the material. So all that's left to do is to summarize. And really there isn't much left to do with that either. Because I've beaten away on these points several times as we've been going through all this stuff. So you may be sick of hearing it by now, but let me just reiterate the main points. This is where we started. And we've been working sort of within the structure all the way along, having identified what the design process is. And you take 2 steps forward, and maybe now and again you have to take 1 step back. This is part of the iteration process. As you make a gradual progression from left to right, you gradually make your model more and more accurate, at the price of making it less simple. And the hard part, of course, is to make those optimum trade-offs as you go along. But we're starting from a difficult position as design engineers, because not only do we not have enough analytic equations to solve for all the unknowns, we have nowhere near enough. That's why it's a tough problem to assemble all the extra information that's needed. But the very first thing to get used to is reversing your attitude. Taking a positive attitude instead of the negative attitude that it's going to be a horrible mess to work out all this algebra, and I'm probably going to get stuck anyway, so I'm not going to bother. I'll just choose some values and twiddle things. So all I've tried to do during all of this time is convert your attitude from negative to positive. That's all. I'm not saying anything that you've learned to do otherwise is wrong or no good or not useful. Of course, it's useful. So I'm not saying don't do any of those things. All I'm saying is you can be even more powerful by getting the benefit of the analytic stuff that you may have discarded because you couldn't make it work. So it's doing nothing but expanding your horizons, and it's not suggesting that you give up anything. The only thing I'm suggesting you give up is the attitude to the analytic stuff and the conclusion that it's no use. And I already said at the beginning, you actually have to unlearn a lot of the things that have been ingrained in you for a long time. And I sort of hesitate to put it in the terms of this example, but maybe after we know each other well enough by now that I can say this. Try to treat this course as technical therapy. You have to undergo a sort of Freudian regression. You have to go back to these very earliest things that you learned and unlearn them. Like all the things the mathematicians told us. And it's not because they're wrong, it's because we have a different goal. You have to get an answer somehow, even if it isn't exact, and you've got to do everything you can to get that answer. So all of these principles and attitudes that have been drummed into us from the beginning, because the people who got to us first were the scientists and the mathematicians. We don't hear from the engineers until it's too late. So that's, in a sense, what we have to do. We have to go through this regression, and the first thing we have to do is understand what it is that caused the problems down the road, which is what's holding us up now. The problems go back very deep. And so we have to readjust to a different attitude, which is just what the Freudian psychology is. You go back and you understand where the problem came from, and then you restart. And that's exactly what we have to do with this stuff. And there's nothing wrong with that. It's just too bad that it had to happen so late. So, going back also to the very first picture here. This is the very first one I showed, where I established the premise for all of this stuff. You get force-fed as a student, and you go out into the real world and you fall off the cliff, because the first time you try to apply all that good stuff, you get stuck. So you abandon it and you restart, and you begin the much longer process of learning by experience and all the other empirical methods. And again, there's nothing wrong with that. It's of course valuable and important. All I'm saying is, let's try to reduce the size of this cliff, so that when you get out of school, you don't fall so far, and maybe you can maintain continuity of slope. Avoid a discontinuity of the first differential. That would be nice if you could do that. Well, unfortunately for all of us here, this is too late. So what I'm saying is, even if you're starting down here, you can still increase the slope. Now, nothing's free, no free lunch. There are prices you have to pay to get the benefit. And in this particular case, if you're going to get the benefit of these techniques and shortcuts that I've been telling you about, you're going to have to practice them. No one else can do that for you. In other words, I can't solve your design problems. All I can do is offer you methods that give you more power. You're still going to have to make the trade-offs and the choices. And that will always be the case. All I'm trying to do is give you more choices and greater strength in making better choices. That's all you can hope to do. And that's just as well anyway, isn't it? That I can't give you the answers. Because if there were a unique answer to every design problem, by the time we'd done it, there wouldn't be anything left to do, and we'd all be out of jobs. So, this is the part that's left for you. And in this concentrated presentation, there's no way you're going to retain all of this stuff. And also, I feel it's okay to say it at this point, no one's going to get more than 10% of this stuff. And that's not an admission of failure in any way. That's normal. When you hear new stuff, you don't retain much of it, even if you do practice. But each one of you will retain a different 10%. I can already see. You've latched on to the part that's relevant to something you know already or you're working on. And all the rest of it passes by. But later on, you'll come across something and you may remember, well, there's something relevant to that might be useful. Then you pick up some more of it. And there's no way around that. You can't do it all at once, and you can't become instantly capable and competent in all these methods. Which is the same thing as saying, if you have to read a technical paper that's written in Russian, it's too late to start learning Russian. Or, in other terms, the funeral directors are always telling us to plan ahead. And it's the same thing here. Because when you need it, it's too late to start learning it. You've got to have that practice ahead of you so you can jump right in and use it. Otherwise, it's of no value. And that's going to be up to you. But that's the bottom line. Now, actually, you're going to have an advantage. You've got it all on tape. So when you feel like it, or when you come across something else and it triggers something to do with this, you can go back and hear it again and get another 10%. So I'll leave you with that.